So Paul has suggested I'll talk about what is it that we're doing in the area of AI. That's a very hot topic. And the whole subject is getting excited about AI. So in order to get somebody excited, you cannot have a canned presentation. That's not what I'm doing. I want it very much alive. I hope you will be asking questions, interrupting me, because then I know what specifically picks up your attention and where I should go deeper. That is based on, so Paul suggested I should talk a little bit about myself. My specialization is probably mathematics and programming, and we've been doing a lot of teaching lately about the last 6 years. We're still trying to write as much as code as we possibly can, but we're also doing a lot of teaching. One of the things that we're doing is a company called Intuit that I'm sure you've heard about. They decided to change the whole company. They want to make the whole company AI-driven company. Now, as I will show you later, AI is the thing that you need to claim you do, even if you don't. But they really want to do it. And so this is a product of that cooperation. They ask us to design this program, how to change the company around. That's what we're doing in the middle. It wasn't easy. It wasn't right away. So let me start here. This is a going over this class. That's real life. It's improving all the time. So what I want to do is show you the demos as we're going, and that will be at least instead of the labs. In the real class, of course, you would be doing the labs. So these are the goals. We want to find out what this machine learning and AI is, and then gradually get excited about this. But there is also one other goal, and that's I want you to be able to talk about this even if you don't know what you're talking about. That's not something unusual. Here is a book. This is the cover of the book on the right here. That is called How to Talk About Books You Haven't Read. The author of the book is a professor of literature. So he kind of knows what he's talking about, but even he says that he often finds himself in a situation where he needs to talk about something he doesn't know. That's not a problem, he says. His students always do this. So that's what I borrow from this book. I want you to be able to confidently talk about AI even if you don't do it as yet. And that is yet another kind of unstated goal of this presentation. So that would be our usual introduction. We're skipping this. Instead, we're going to the main presentation, which is right here. And we'll start here. Now, once in a while, I'll have to jump to another one. That's fine. That's because that's our major goal, is to get you interested and excited. So let's start talking about what is this data science? Why is it important? Why would you like to introduce it at least to yourself and then maybe later on to your organization? So we are all used to what is called data warehousing. We're all used to what is called ETL, extract, transform, load. And this is still here. It doesn't go away. It can tell you what happened. It can say, this is what your sales were last month or last year. Then you can ask the next question. You can say, why? Why did it happen? And it will allow you to drill down and say, well, this is why it's happened. But if you ask the next question, if you ask, what will happen to me next month? Or what will happen to me next year? Then you cannot do this. The best you can do is you can say, well, I noticed the trend, 10% going up, but this is very weak. That's not really a prediction. So here we have a new phenomenon. People use this data science, which allows you to predict the future. And the better you can predict the future, the more money you can make. That's how one of my friends formulates it. He is a vice president of the big telephone company, and he also teaches in a college in Chicago because he wants to get in touch with people and he wants to hire people. So his students often get hired. So this is what happened in just the very recent few years, exactly 2012. It's that the guy who used to be called a geek, a statistician, mathematician, and other such stuff, and who wasn't very popular at parties. He became suddenly all the rage. What happened? Well, what happened is, first of all, is that a certain guy by the name of Jeff Radenbacher, who used to work at this time at Facebook, he invented the term, and he called it data scientist. That didn't exist before 2012. From then on, you have colleges that offer degrees in data science. You have a data science qualification. You know what? Since I'm sharing the screen anyway, let's do this. Let's go to Indeed. Indeed.com, that's where I usually do my investigations. And measure how many people want to hire a data scientist. Right? Let's do it data scientist in all over the US. So what we see there is 8,000 jobs, right? And I didn't prepare, didn't invent. Let's do a comparison. Let's say a statistician. A statistician. And then, okay, about 12 times less. So you see, I didn't invent, I just tried to improvise. But this is what happened in the recent years. So we want to see why, what exactly happened. So as I said, the term existed for a long, long time. Jeff Radenbacher invented it. But by now, there is another phenomenon. You need to say you're doing AI. If you don't say this, then you're out of the market. Because let's say you go to a shop that cleans your shirts, it has to say that it's using AI to clean your shirts, and in fact, it finds the best possible compound to clean your shirt and so on. That's just a trend. And therefore, this is important this way. But this is also important in the real way, that gives you a way to foresee the future in many different ways, not necessarily finance, but let's say your Google Maps, it knows where you were, knows where you will go. It often helps you with setting up your route, and Uber and Lyft, they all seem to know more and more about you. So not only this is real, I'll show you exactly what is real, but it also has become a norm. That's what you expect. All of your consumer products are very smart. So now people begin to expect this of the enterprise software, which is known not to be that smart as yet. So this is where we are. I have a whole explanation of what each company does about use cases. I don't want to do this now. I really want to give you the, not what others do, but what the science allows you. So I'll skip this one, but I'll go into the machine learning, and I'll show you exactly what it is, how it works, why it works so nicely. So let us stop right here. And by the way, if you want, you can just ask. I'll send you this slide deck about what others do. What can you learn from Uber? What do they do? What can you learn from Airbnb? Because each one of them is very open about what they do. Okay, but this is what we want to talk about. No, not this one, but this one, right? So first of all, what is machine learning? We need to ask my daughter, who does cartoons, and that's machine learning according to her. More seriously, machine learning is this. Machine learning is where you stop programming. You don't want to code anything anymore because that's not the best way, you heard. Instead, you give the computer the data and you let it figure out exactly what it should do. I'll give you one example before we go into self-driving cars. The example is that there is a startup that will write the code for you. To do so, it will ask you for a description of your problem, and then it will go to Stack Overflow, find the relevant examples, pull them down, combine them into your code, and give you the beginning of the code. So that is more or less learning from the data that is available in the world, not the prediction of the futures yet, but learning from this. A more explicit example is self-driving cars, which are here. They have millions of driving hours already. And here's how you could do it. One example how you could do this is by just reading the booklet. There is a booklet that you need to read and know before you get the driver's license. So you can read this booklet, that's the first approach, and formulate every rule. And after that, you need to write it down in the code, and that car will be able to perform according to the rules. That's the first approach. Actually, it was tried. I'll tell you when it was popular. But today's approach is this. You let the computer, you put it right next to yourself in the car. Now, when I say and put it on the right, then I am explicitly saying I'm not in England, but in England I have to say you put it on the left. So you put your computer right near to you somewhere, and you let it record all of that, what it sees. You also record your reactions. That becomes your data. You analyze this data, you match your reactions to what the computer sees. We'll talk about exactly what it sees, that's later on. But you let it predict your next reaction. So out of that, you get a self-driving car. That's a bit more complex than what I explained, because in order to analyze the scene, you need to record it 60 frames per second. So that will be pretty fast computation. Then you need to analyze the picture, and the picture you analyze with what is called deep learning neural networks. We'll get to that. You break the process into a few steps. First step, find the contrasts, find the circles, find the straight lines. Then you combine them into this is the wheel of the car, this is the body of the car, and then you combine it. Oh, that's the car. I know what that is. And then you also find people. All of that has to work in a pretty fast time, but today it does, and it actually works faster than the human. So I personally wouldn't be surprised if eventually human driving will be found very dangerous, and so will be outlawed, and only the computers will do that. So that is one example of machine learning. Another more formal definition of machine learning is this. You need to define a certain task. Let's say a task of talking to you like a human. You're trying to fool a human. You're a computer. You're trying to fool it. So that's your task, to conduct an intelligent dialogue. And you give it the data. The data is the experience, E, of all of the previous dialogues that you had on that subject. And most importantly, you need the measure P. So you need T, P, and E. T is the task that you're trying to make computer do. P is the measure of how good it is doing. So if you can improve this, if you can improve the probability that your program will convince you that it is a human, then you're machine learning. You're improving with your experience, and you're learning from that experience. So that's a different definition. Now, at this point, I want to show a couple demos. One of the demos is the Google dialog. That I don't want to show because that requires listening. I'm not sure how it will work, but I will give you the link and you will be able to listen. Instead, I will just describe what it does. So let me do this. I need to get to my place where I store all of those demos. And I will give you the first link. Here. And this is this. It's that link. If you have not ever heard it, then that's your chance to hear it for the first time. Now, what I want to do is I copied this. I want to paste it somewhere on the meeting. Let's see if I can do this. To save the time, I'll just send this to Paul. He'll make it available. I think that's the easiest. But what's important is that in this situation, when you listen to this, you will see that the computer indeed fools a human. It's able to talk just like a human, and it does this by, notice when you're listening to it, you will see that it's trying to pretend it is stupid. So in order to fool humans into thinking that this computer is really human, the computer imitates stupidity by not presenting things straight. It can talk straight, it can talk fast, but instead it adds, well, it adds those things which are characteristical human. Other than that, it also imitates a little irritation when it's not completely understood. So these are two wonderful dialogues which are well known. Another thing that I will show you is the example of the very first such system. And that is something that is still very relevant today. So one of the first systems which illustrates the very first approach. And since I'm sharing the screen, that's a perfect situation. So the example that illustrates the first approach is this. It is a program that encodes all of the rules. So it's the first approach where you would read the booklet on driving and then code these rules. In this case, what I'm allowed to do is, I'll make it just a little bit smaller like this. There you are. So that I can ask questions. So let's ask Eliza some questions. Let's see, do you work? What it will answer. Because we were discussing you, not me. Okay, well, I want to insist, but do not here. Okay, but. Okay, so you see what it's doing. It has asked some of psychiatrists, that's what the program says at the top. It asked them exactly how do you conduct dialogues, and then if I go into the favorite subject, mother, she harmed you, right? So there you are. She will ask you the questions that the psychiatrist would ask. So here's another example of the early approach to this. And let's continue, because now I'll show you what people do exactly. These were all great examples. I'm sorry, I started the wrong slide deck. The one that I really need is the other one. That's where we are. So these are the definitions. Now we want to do a bit more real. That talks about, you have defined your machine learning. All of the machine learning will be essentially the same way. And the next step that you will bump into that's unavoidable is somebody will say, well, you're reading a book on AI, you're reading a book on machine learning, here's your chapter on linear algebra. You'll be a bit surprised because you didn't expect. Usually in the class, I ask guys, how many of you had linear algebra in class? Depends upon the class. Most of the people say, yes, I did. And then I ask them, well, who can define what a vector is, what is a matrix is? Sometimes people do, but then I ask them, can you multiply? Can you multiply a matrix by a vector? And that's 50% of the people drop out, maybe more. And then I ask them, well, can you invert a matrix? So, well, some people can invert a matrix even now, but most cannot. So the question is, why? Why do I need to even think about linear algebra if I'm talking artificial intelligence? Well, it turns out that it's very easy to formulate all of the machine learning problems in terms of linear algebra. Then I showed them, this is what you would do. It's not all that hard. Let's say you have a house and you want to predict the price of the house. Then you will choose the features. The house may have certain number of bedrooms, certain number of bathrooms, maybe a few thousand square feet of living area. This will all be H. That's the house and its characteristic number 1, number 2, number 3, number 4. Well, you can do it like this. But first of all, it's a lot to write. It's not concise. And secondly, it won't be that easy to program. Instead, if you put all of your data into a matrix like this, then you can formulate, here's the complete problem, here's how I calculate all the prices in terms of multiplication between matrices and vectors. So if you get this and you accept that you need to refresh your linear algebra, or I would prefer to do it the other way around. Don't force people to learn math now if they never wanted it, but rather explain it as you go. That's what I would prefer to do. In any case, you will be able to explain all of the AI in terms of linear algebra, and then the amazing thing will happen. Not only you will be able to communicate with other people, but your computers will run about 300 times faster. That is because if you program everything straight, just like it says here, H1, H2, H3, then you're telling the computer exactly what to do. This is called imperative programming. I'm telling it exactly what to do. That's slow because the computer cannot optimize anything. If I formulate all my problems like this, if I'm saying, here's your matrix A, and here is your price vector, then the, let's say, Python program would work about 300 times faster. So this is how some math comes in. Math is a sticky subject. I personally like it, but I understand that not everybody does. So if we have mounted this obstacle, now we can look at what happened and what is happening now. So what happened is that people always wanted to do machine learning. They always wanted to do artificial intelligence, and they succeeded in some measure. In the 60s, the first computers were quite available, and here's how that first guy whom I showed before, this guy, he taught the computer to play checkers. He liked checkers. So what he did was to make the computer play against itself, and it played about 100,000 games. Then it would simply calculate the statistics on which positions usually are part of the winning game. And it would always prefer to take those positions which it knew were part of the winning game. So a very specific combination, but the computer already played checkers better than the designer. But then what happened is that people were sometimes overexcited. For example, in the 80s, people were overexcited about what artificial intelligence can do. And at this time, artificial intelligence was exactly this Eliza program that I just showed you. This thing, that is what artificial intelligence was in the 80s. So they thought that they will encapsulate all the experience of all the experts, and there you are. You take the people out of the equation. The problem is that it's very hard to do it this way. You're not really learning from the data, or at least the computer is not learning from the data. You are learning from the data, and that is not very scalable. So the results were never above 80%, and at 80%, it's pretty much garbage. So it didn't quite work, even though some people were enamored of that. I know a company that has 30,000 different rule-based compute experts. Well, that's not what they do today. But then came the 21st century, and here's what happened. You have big data. So in this big data, you have a completely different power equation. Here's what it represents. Let's say on the bottom here, I have the scale of computing, the scale of the data that I'm dealing with, and on the top, I have accuracy. So first of all, very often you now can get the answers directly from the web. How did IBM win the Jeopardy competition? It did so by collecting all the answers from the Wikipedia. Of course, it had to understand, this is where this blue line comes in, but a lot of information is there. Secondly, you need to learn from this information. And this is what was happening. This green represents the standard methods. For example, Eliza, I would call this. That's a standard method. And let's say you're trying to fit your price to the known data. That is what is called linear regression, a standard machine learning method, which you need to know. You need to start there. But then there was a new approach called neural networks. And this new approach wasn't quite working, so it was a research approach. And then there were many ups and downs. Somebody wrote a book that the neural networks will never do it, and the government took away the funding. In the end, however, this is what happened. The computational power of clusters and big companies, and eventually available to everybody through the cloud computing, became much bigger. With that, you could learn much more complex behavior, not just a straight line behavior, not a few questions and answers behavior, but the real behavior of the systems coming from real world. Once you had this, and this happened according to some 2006, when the first neural network has beaten the best of the other approaches known at this time, which was SVM, the support vector machines. Some say 2012, because at this time you had these neural networks really prominent. And now these neural networks give you better answers. So neural networks are harder to train. So you use both. For some approaches, you still use this green line, you use this. For some, you use neural networks, but the results are amazing. You also saw how the credit card fraud works, because almost everybody gets their card stolen, and then the computer system detects that pretty well. You also see recommendations all over. You know that Netflix is doing, I think it was 70% of their business through recommendations, but today probably much more, because you also get the push notification that something that it knows you really are interested in, that something became available. Like, let's say I have a specific author, that a movie director that I love, because I'm learning Chinese, and he does the greatest Chinese movies ever. So today I'm getting, you know what, 5 years ago he did the last movie, today he's doing another one. That's recommendations. That learns from your behavior, it learns the available products, it matches them. And then on and on, you have people who are working on custom medical prescriptions, so that that particular prescription will work exactly for you and will cure exactly you, and so on. So you do get those amazing results. The theory is available, the technology is available. You can either use it in the cloud, or you can use it on your own computer if it's powerful enough. So that's where things are today. That's what AI does, but we will still continue a bit more. That's a diagram that helps you understand where things are. So here we have artificial intelligence in general, all those smart systems. And that includes everything, even things which are simple like this, again, Eliza. It's not something that machine learning would do or deep learning would do. However, Eliza is kind of coming back as well, because now that you can understand the question much better. So the problem with Eliza was not that it wasn't very smart, but it couldn't understand what you were saying. So today, you can learn what you are saying from deep learning and then apply the general principles. In other words, all of that technology comes together. You have the standard machine learning, like straight line predictions, and you have deep learning, like lots of different ideas and exceptions incorporated. So that's the complete picture. And now we need to talk about neural networks, because this is where the most impressive results are. The machine learning has been known to the world from the 80s, maybe even before. Today it's everywhere, but neural networks really began to shine from 2012. So first of all, what are they? A neural network imitates the human brain. It says, I know how human brain works. And it says, I think it works like this. A human brain has about 100 billion neurons. These neurons are little cells, and they communicate. They talk to each other through little electrical impulses, and they process information simply by training, meaning that, let's say, a child learns to see, and at first, that child sees shapes, not perfect, but then the network of neurons adjusts, and it gets a better and better picture. And then it begins to train. It verifies that what it sees is what really is. And so the child now grabs the toy much better. That's the idea. From then on, people decided, let me do this. Let me imitate this artificial neuron, and let me do the processing from one layer to another, like this. And let me first detect these features, then detect combination of these features, and then detect the faces. So that particular variation of an approach of neural network is called CNN, convolutional neural networks, and it uses a transformation to come from here to there. The result is, you know, Facebook introduced the face recognition in 2015, really. By now it's a norm. Of course they recognize faces, and of course they know, and so on. So this is the whole progression. That's what happened. Initial expert systems, you had to do everything. You would read the book and try to program the knowledge into a computing system. The next is classical machine learning, where you wanted to say, I know how to characterize a house. It's this. It's the number of bedrooms in a square feet. And then from then on, you could do a pretty good prediction on the price. But then people went on. They said, I want the computer to understand what it needs to look at. So it should figure out the features. And then finally they said, it should look at the features and then come back and reevaluate this. I'll give you an example. let's say you're trying to do a face recognition, and it is a known problem with the image recognition that if your face is partially in the shade, partially in the sun, then the system will probably recognize the part in the sun because it's very well lit, and by contrast, the one in the shade will be missing. So maybe the system will find the person's mouth, the person's eye, but not the other eye. We're here. Then it goes and it adds the features, and now it understands that that is a face, but one eye is missing. So it will go back and it will say, well, I understand it's a face, where's the other eye? And it will try to find it this way. So this is already giving you very practical results. Now, at this point, if I were to teach you the technology, if we would go through the labs, at this point, I would say, guys, you know enough. You know how to predict the price of the house. You know how to predict if somebody will get into college based on his grades. You even have an idea of how to do machine learning in neural networks. So let's do this. Let us have a competition. You'll break down into teams. You'll present me an idea of machine learning system you would like to build. And at this time, I don't ask you to program it as yet. But of course, we don't have the idea to do this right now, but people really love it. Besides, people really love competition. Now, that's the complete overview. The rest here, we'll just go through the terminology, and the two most important terminology points are here. One is called supervised learning, the other one is unsupervised. So what are they? That's pretty much all we need to know. Supervised learning is where you know what the answer is, and you give it to the computer. One example is house price prediction. Here are 30,000 houses that I grabbed from Zillow, and here is the price that they fetched on the market. So that's the answer. If now I'll ask you to predict the new price, you will say, based on the previous pricing, I know what the new will be, and you can get to the accuracy maybe of 90–95%. That will be decent. Another example of supervised learning is where, you know, these are the bad attacks, these are the good attacks, these are the bad guys in the network, these are the good guys in the network. Tell me about this new person that I don't know. Is he good or bad? If I gave you all the previous results, you can say, well, he looks very much like the good guy, so he must be a good guy. But the unsupervised learning is where you do not know the answers. Nobody tells you, and they're not available. So for example, maybe you have lots of news, but you don't know what they're about. You want to cluster those news, and you want to say, well, there are the 10 groups of news. They all go together. So here's the first one, the next one. Then if you have an additional label on one of them, you'll say, well, the first one was health. The other one was maybe technology. So these are the two major things, supervised, unsupervised. Unsupervised has its role. Let's say I don't know what the attacks are. We're always talking about the new attacks. So I'll be looking for unusual behavior. And unusual behavior is pretty hard to define. So I'll tell the computer, can you analyze this data? And can you say what is normal and what is abnormal? And then abnormal is what you can help me with, because I cannot program that. I don't know what the characteristics will be. But if you can learn it from the data, then great. So these are the two ideas. Supervised learning, which is more prevalent, gives you better results. But unsupervised learning is also important because it gives you the knowledge that you wouldn't even have the other way. So with this, you can also tell me, well, my problem is supervised learning. I'll give you some examples. So let's say one student tried to predict how long will it take him today to get home. He's in California, lots of traffic. Another guy tried to do the perennial favorite, the stock price prediction, and he did almost 100% prediction. The problem is he did it for some wrong company. But other than that, he did well. Then I remember one approach. The guy said, let me predict how much this applicant will claim that he is sick and stay away from work. Not necessarily sick, whatever he says. In other words, predict the absenteeism. When I'm hiring people based on all the data, can I say that this guy will not really do good work? So these are some examples of what comes up when I do those hackathons. I don't call them hackathons. Today, companies all overuse this. They think hackathon is a way to make you people work harder for free.
But if you present it in a different way, like here's a competition, and give it to them very offhandedly, then people like to do good. They like to compete. So the last demo that I will show you, well, can you show me the neural networks? I understand how price prediction would work. The answer is yes, I can show you the neural network. For that, you go to Playground TensorFlow. So what is this? TensorFlow is a new library for prediction, exactly that. And it is done by Google. It's extremely popular nowadays. This is the same library working right there in the browser. So here's what you do. Let's say there are one of those 4 possible problems that I'll present to you, the simplest one. We have 2 groups of points, the blue ones and the purple ones. And now the new point comes in. Can you tell me, will it belong to the blue cluster or to the purple cluster? So here's my neural network, but I'm asking an extremely simple question. So first I'll do this, then I'll explain what is I'm doing. Each neuron is essentially an implementation of the regular machine learning. So if you know regular machine learning, you'll understand that each neuron is one simple decider. That's called logistic regression. Am I right or am I wrong? Is the answer yes or no? Is the guy blue or orange? These are the 2 inputs. I have X and Y, and with this, I want to predict, will that be orange or blue? So all I need to do is start on neural network training, okay? But that was so fast, it found the answer right away. Let's stop it right here. So you see a few things here. On the top, you see all of the possible parameters that you can set when training the machine learning. I'm skipping that because that will be too deep for now. But on the right here, you see, yes, it found the border. This is the distinguishing boundary. Let's do this again. Let's stop it, refresh it, and please watch how it finds it. Boom, it found it now, right? So it took a little time. It wasn't obvious right away. At the right here, top right, it says the loss. The loss is the most important word. It says, I'm replacing my data with the function, with the machine learning. So how much am I losing? How much precision do I lose? And the neural network, unlike other algorithms, keeps training. You can say continue. And it says, these are my iterations, and I keep doing it better and better until I come to the total loss of hopefully 0, completely 0. So that's what you're doing, you're training them. Now you will say that that's probably all too easy and I don't need any neural network for that. And that's true. So the most complicated problem, well, let me do not the most complicated problem first. So let us say I have these points. Now it's not as easy. There is no straight line that will divide blue into one group and orange in another. Essentially, you have exceptions. You're saying when x1 is big and when x2 is big, that's blue. When any one of them is small, then this is orange. But this is an exception. If all of them are small, then whatever you thought you knew is wrong. It's also blue. So how do you do this? That is an exception. Well, what you do is you allow exceptions. And exceptions means you add more layers of decisions. Something like this. And that means start with your linear decisions, but then complicate them. Add exceptions. Let's try to see if that will work. You see, it's trying to find it. It's not really succeeding. I think it needs to know more, and its error is still about 1/4. That's pretty bad, right? So we'll stop that. We'll try to do this. Let's add a little bit here, more deciders in each layer. So let's see if we can find it now. Boom, there you are. It did find it, right? So it said, and it keeps training, trying to get to little loss. But by now, 0.0, okay, 0, no loss. So that's where we will stop. This is a tool that explains. It's still not a tool for you to do the work. That would be something like the TensorFlow library itself. But it gives you the idea of how you can play with the neural networks, what they do, not exactly how they train, but the fact that they do train, and they come up with final results. So that is what I wanted to show today. There's a lot more here. One of the things that we do is at the very end, we show what are the best books. Okay, we've done this 2, 3, 4, 5 days courses. Now you can actually do it, but still there's a limited amount that we were able to put in this. And then I show you the best books. So let me do this. I think I have a minute maybe to show you that slide deck. I close this, that's done. This is also done, but there should be a conclusion. And in this conclusion, when you ask this question, so what now? The answer is, here's what now. This is the great book that allows you to become a manager on this project, because it gives very high level advice coming from the expert. So high level, but expert high level without the technology. The other book is totally the opposite. It's all the technology that you can get, and the authors are it's the people who are inventing all of that, so they really know what they're talking about. That book is not for the weak of heart, but it is the definite book. So if you want to check whether it's true or no, you go to this book. Another one is one of the tools that you can use as Spark. So there is a great book on Spark today. And finally, there is a big theme that people often miss by Zheng. It is, well, before you even start machine learning, how do I choose the project? How do I choose the features that I need to look at? What's important? That is a step that's very often missed in machine learning. People jump into programming. They don't think. So that allows you to think. These are the 4 great books that I usually present at the end. I'm saying these are the things that I do recommend you should keep in mind. If not read right away, now keep in mind that these 4 today are the best. They are all published this year, so they're quite current. That is it, and now I'm very much open to the questions.
Mark, thank you very much. It's Paul. Hopefully you can hear me. One of the questions that comes to my mind, and obviously I'm not a developer, I'm not an engineer, but I do have a sort of gut level question. If you are an engineer, a project manager, someone working in this field, and someone is talking about a machine learning, big data, AI type of project, what type of data would jump out to you as the kind that would be a project that will never succeed? I mean, this may be a silly question, and one that will almost always succeed. I mean, obviously, we're at the early days of this, so I'm sort of at a gut level, when someone says this is the type of data set we have, and then we want to make it, enable it in the machine learning world, what's the kind that seems to you at this stage to be a project that's bound to failure, and one that is bound to succeed, if there is such a thing?
I think it's a great question. And there are good answers. Most of them would be coming from this book. The answer is that, first of all, you need enough data. And the practical number is, let's say, 5,000 points. If you have that much data, you can already do some machine learning. The second question is that if it doesn't succeed, you want to know as early as you possibly can. Before you start the project, you don't even know at all. So your project should be 1-2 weeks at most to start. And the rule is use the simplest possible machine learning that you know. All of them are close enough. Maybe the best will give you 10-20% more precision than the worst. But you should see that that data makes sense, that you are able to process. And there is no great rule for saying, oh, this data is good, this data is bad. All data is good. But however, what you could do is this. You can go to Kaggle, and that is the place where all of the data scientists hang out. So if I'm still sharing the screen, I'm going to this Kaggle. This is where you can see what people have done. You can search for which projects were done successfully, which were not so successfully. You can even see the data itself. You can download a lot of different data sets by going here, and you will look at where are the data sets. So first rule is there should be enough data. Next is you should do a quick prototype to see how does it work, what does it bring you, can you even predict something. And then the third one, let's try it. Let's go to some of the known projects, known data sets. Let's look if I can find something similar to what I'm looking at. Is that your question?
Yes, that was it. I'm also sort of on some level, as you were saying, no data is bad data, but obviously there's visual data, there's text data, or oral, sound data. Obviously, some's going to be more difficult than other to interpret. That's also what I'm thinking about on some level. Is that something that?
Yes, I agree. So the simplest data would be like, these are my sales items and these are my prices, and can I predict something about to my advantage? What will happen if I raise the price, for example? That will almost surely succeed because it's very well structured. The next one you mentioned, text. For text, you need to know a bit more because you don't want to reinvent the wheel. You need to know what are the usual approaches to analyze text. And you'll find out that there are very well-known approaches. For example, there is a word-to-vec. That's the method people all use today to analyze text very precisely. So you need to know a bit what it does, and then you're back into analyzing that particular text and training your model. And then the next one is images. So with images today, it's probably neural networks because that's so much more data than you used to, then no other system comes close in the performance. So you see the answer is different for each of the data type. There is a particular technology that works very well for each one of them. And then let us say your data is moving. Well, let's say it's a stock price that keeps changing, or maybe it is a speech that you're trying to understand. You're building a robot to talk to, and it keeps talking. So for that, there is a special kind of neural network that allows you to work with the data that is a time series data that changes all the time. Nevertheless, you're able to understand. Was that your question?
Yes. I'd also like to ask anyone who's on the call who is involved in a project that is relevant to this, if they have any particular challenge and can, obviously without disclosing anything about the project itself, but something that they can text or message on the side that would be illuminating to them in the project. We'll wait a few minutes for that. Okay, and if not, that's fine. Again, we will be doing other programs on this subject and hope to cover topics that are of interest to you. Again, if you have others that are of particular interest, just let us know by sending an email to helpdesk@starweaver.com, and that will help us figure out what best to do on an ongoing basis. Again, we have a series of programs that are coming up. You will recall and go to our website to find them. If there are no other questions, we'll wait another minute or so to see if they come in. And then, Mark, great project, great webinar. Thank you for your time.
Okay, thank you very much, Paul. And I'm sure that people listened. I kind of have a feeling. You developed that feeling to the listener now. And I think they did. It's just that it was a lot of information to digest. They might come back with their questions.
Yeah, please do. Again, we will do more projects on this. It's kind of a very straightforward way of addressing projects you might be immersed in. And thanks again, everyone. Have a great day. And this recording will be available very shortly on our website.